Good morning to one and all present here. I welcome all the participants to this sixth day short-term training program on nanotechnology and functional materials phase 2. Now we are going to start this sixth day and first session. Once again, thank you for joining with us. Now let me introduce our eminent resource person, Dr. G. Anbuchedian sir from SRM Valiamai Engineering College, SRM Group, Cotton. He has completed doctoral degree in Anna University in 2019. He has completed ME Engineering Design in Anna University in 2006. He has completed BE Mechanical Engineering in Madras University at 2004. His field of specializations are composites, metal foams, magnesium and hollow glass microspheres, reinforced syntactic foams. He has published more than 9 scientific research articles in international standard journals. He has attended more than 8 national and international conferences. We are honored with your presence, sir. Now I request our resource person to proceed with the session, sir. Professor Anbuchedian, sir. Now you can start, sir. Yes, sir. We are seeing your presentation screen, sir. But voice, it is not audible, sir. I think you need to unmute your audio, sir. You are in muted condition, I think. Sir, now you can speak. I think you are in unmuted condition, sir.
The screen is. Could you able to see the screen, sir?
Yes, sir. Yes, sir. We can able to hear your voice, sir, but the screen not yet shared, sir.
Sir, just.
Yes, sir. Yes, sir.
Now see that.
Presentation mode, it is better, sir. Yes.
Okay, sir. Okay, I'll see. Sir, now see the audio.
Audio is okay.
Hello,
sir.
is it okay now, sir?
Yes, sir. Yes, sir. Audio
Hello.
is okay. No problem, sir.
Screen is.
Screen, if
Okay,
it is
sir.
a presentation mode, it is good, sir. We are seeing your forthcoming slides also.
I shared the screen now.
Yes, sir. We are seeing your shared first screen, sir. Recent advancement in nanocomposites. If it is presentation mode, then it is okay, perfect, sir.
Okay, so shall we start with it? First,
yes, sir.
first
Yes, sir. Yes, sir. Clear, sir.
Okay, shall we start, sir?
Thank you, sir. Yes, sir. Please,
Okay.
please.
Okay, so very good morning to one and all present here. So based on that title, Nanotechnology and Functional Material, I have chosen the topic, Recent Advancement in Nanocomposites. So now recent days, it's nanocomposites takes place an important place in development of improvement of technology and modern civilization, especially for mathematics composites and polymer matrix composites. So based upon that, here I have given some came here to give some research work based upon the nanocomposites. So these are the introductions that I'm going to deliver. Give these are the things that I'm going to deliver here in the present scenario. There is a evaluation of material, composite materials, metal matrix, nanocomposites, and I'm not going to deeply elaborate what are the types, classifications, all those things. But I'm going to give some introduction about that. Then, and after that, we have done some research work based on nanocomposite using aluminum and magnesium composites. Okay, so that is the thing. So based upon that, we'll start our introduction with the evaluation of materials. So it is well known to all how the material has been evolved. The material has been evolved from natural to man-made. Okay, so from natural, the people used stone. So that is the Stone Age. The people used the stone as a weapon to kill animals to have their foods. After that, we have evolved to Bronze Age. That is extraction of copper and its ores. And then finally, they moved to Iron Age, the extraction of iron and its ores. In the heat treatment process has been carried out. After that, they have moved to Steel Age. So in that, Bessemer and open head process has been used for production of steels. And finally, they moved to Silicon Age. So in that, the electronic components and the computers, automations, all this come to the market. So from this, it is clearly known that the material takes place an important role in development of technology and modern civilization. So it is well known that the designers have the designers have kept eye on finding new materials because the conventional materials cannot perform to its maximum limit. So they have found new materials that should withstand high performance, efficiency, reliability, lightweight, and it shows combination of properties. And also at the same time, these materials should withstand extreme environments such as high temperature, high pressure, low temperature, low pressure, and highly corrosive. So these are the things they have considered for finding of new materials. So in this condition, the researchers have found so much of materials to meet the technology requirements, and hence they cannot obtain the rigid property requirements by using a single type of material. So considering that, they have decided to go for a combination of materials. So that was evolved as a composite materials. So I have given the next we go for composite materials. So there are a lot of definitions available in composite materials, but here, so technically, composites are heterogeneous at microscopic level, but statically homogeneous at macroscopic level. So here I have given that. So apart from that, I have given another definition. Composite materials are those which are formed from two or more materials producing properties or characteristics that could not be obtained from any one material. Okay, technically we will tell that composite materials are heterogeneous at a microscopic level, but statically homogeneous at a microscopic level. So we can see that various amount of materials that have various dispersed phases that exist in the nature, such as metals, alloys, processed polymers. But we cannot tell this as a column composite because their properties are similar to the close of base consistency. So if it is being a composite material, so there should be a condition should be satisfied. First one is the combination of material should result in significant property change. Okay, the combination of material should result in significant property change. Another one is the content of constituents is generally more than 10%. Okay. Next, third one is the property of one constant is much greater than the corresponding property of other constants. So these were the following conditions to be satisfied. So then it is going to be a composite materials. Okay. So here we know that we have different types of composites. We have metal matrix composites, we have ceramic matrix composites, and fiber reinforced composites. And based on the application, the researchers are focused on several layers. Okay. So after that, we'll go for here I have given. So why composites over metals? So here I have given examples when composites when compared with the two metals, one is aluminum and steel. And here, the weight reduction of composite is very low when compared to that aluminum and steel. After that, the thermal expansion coefficient is also very low. In addition to that, the stiffness of composites has significantly increased, and the strength and fatigue resistance also comparatively increased when compared to that metals. So the advantage of matrix material, the advantage of matrix materials for the reinforced particle is it is able to withstand a high range of temperature with the degradation and loss of strength. The biggest advantage of fiber reinforced particle is for they can able to withstand highest range of temperature with the degradation of loss. So composites materials are mostly used for nowadays the composite materials are mostly used for high temperature applications, so that mostly they won't go not degrading the polymeric matrix composites, so that for high temperature purposes they go for metal matrix composites. So for that purpose I have given here. And metal matrix nanocomposites. So metal matrix nanocomposites, that is nanocomposites are materials that incorporate nano-sized particles into a matrix of standard material. Okay, so the biggest advantage, or we can tell that composite consists of metal matrix filled with nanoparticles. The biggest advantages of metal matrix composites were when the biggest advantages of nanoparticles is we can improve the strength when compared to polymer matrix. There is high strength, modulus, and wear temperature can be improved significantly. And by using nanoscale reformation, so these are the general properties that can be increased. That is, a tensile and compressive behavior can be increased. A minimum amount of ductility can be able to see by using that by inclusion of the nanoscale reinforcements, and it can able to withstand high temperature mechanical properties, creep and wear resistance, including scratch resistance. Dynamic mechanical properties can be improved, and coefficient of thermal expansion, damping, machining, both the dry and wet condition, also corrosion resistance can be increased by adding a nanoscale reinforcement. So, in addition to that, the inclusion of nanoscale reinforcement, the mechanical strength, the toughness also tends to increases. So, metal matrix composites with the polymer we can compare with the metal matrix composites with the polymer matrix. In case of metal matrix composite, it inherent high temperature stability, high strength, high modulus, wear resistance, and thermal electrical resistance. So these are the challenges on facing development of metal matrix nanocomposites. So greatest challenge for wide application or cost of nanoscale reinforcement, the cost of complexity of synthesis and polishing nanocomposites. So mechanical, so here, if the metal matrix nanocomposites, the properties of metal matrix nanocomposites has to be, if it has to be increased, means that it should have uniform distribution of reinforcements and the volume fraction of reinforcement as well as the interfacial strength between the matrix and reinforcements. So as I told you earlier, so the processing of nanocomposites is very difficult because particle agglomeration occurs, or particle agglomeration or particle formation of cluster will occur. So this has to be a major drawback in nanocomposites. So this has been resolved in several factors by varying the effect of process parameters, using stirrer design, effect of process for the stirring design, stirrer times, temperature, and also by using vortex method we can be able to resolve some problems. It is also that the nano-sized particles have high surface area. The nano-sized, due to that, the nano-sized particles will naturally tend to agglomerate to reduce the overall surface, making it difficult to obtain uniform dispersion. Okay, so there is a major problem. So the main important thing is particle agglomeration occurs. So another thing is we increase the percentage of reinforcement. The surface area keeps on the surface area of the particle tends to increase, and hence the particle agglomeration. A minimum amount of agglomeration can be able to see in the matrix material. So that is a thing. Okay. So next I'm going to discuss. So these are the mechanism of nanocomposites. Nanocomposites, so that yield strength of metallic material is stress required to move the dislocations and to activate the dislocation sources. So generally metal matrix composites, they use to strengthen, they use as overall strengthening, enhanced dislocation density, load bearing effects, and grain boundary. So used to strength, are called a strengthening mechanism. So in war-on mechanism, it is the obstacle caused by closely spaced particles to the movement of dislocation. Okay, it is obstacle caused by closely spaced hard particles to the movement of dislocation. So that's in conventional micron-sized particles reinforcement. The reinforcement particles are coarse and the interspacing is large. So it is favored with the high dispersed. So, but in case of nano particles, it is favored with the high dispersed particles. Okay. So next we will see about enhanced dislocation density. The thermal stresses arises around the particles. Example, during thermal stresses arises around the particles. That is, the matrix and reinforcements are generally characterized by coefficient of thermal expansion. The stress level is often large enough to cause plastic deformation. So that's the matrix reinforcement the matrix reinforcement interaction region, thus inducing high density dislocation. So this is the thing that. Next, we go for load bearing effect. The shear transfer of load from soft matrix to the hard ceramic materials. So the reinforced mechanism effectively only coherence, and finally we go for grain boundary refinement. So nanoparticles acts as a heterogeneous sites during solidification, thus giving rise to more refined and a possible eukaryotic structure. In addition to that, the nanoparticle restricts the migration of thermal excited grain boundaries, and due to pinning effects happen during recrystallization. So these were the general things that we go for mechanism of nanocomposites. We call as strengthening mechanisms. So now they have improved. So some researchers have tell that instead of Warman strengthening, enhanced dislocation density, load bearing capacities, and grain boundaries, they'll go for C mechanism and K mechanism. Where the C mechanism is critical flaw size reduced. That is, matrix become refined due to inclusion of nanoparticles. And in case of K mechanism, fracture toughness is increased. Okay, so K mechanism related to the arc curve behavior, that is resistance to fracture versus crack extensions. So they will for strengthening mechanism, instead of this foreman strengthening in this forum, they'll go for C mechanism as well as in metal matrix composite using micron scale is what that it shows limited plastic deformation and exhibits reduction in ductility. So that cannot be happened in nanocomposites. So a minimum amount of ductility can be able to see by adding inclusion of nanoparticle reinforcement in inclusion in the matrix alloy. So these were the metallic materials that are often used for synthesizing nano aluminum its alloy bronze.
Sorry to disturb you, sir. Excuse me, sir. Sorry to disturb you, sir.
Hello.
Sir, your voice is not clear, sir. It is slightly breaking, sir.
Actually, there was some connectivity problem. If is it right now?
Yes, sir. Now it's okay, sir.
Okay, so then I have to keep my mic. Then I have to keep my mic. Okay, sir. Okay, so these were the metal matrix and reinforcement. So these were the common metal matrix used for synthesizing nanocomposites, aluminum in its alloys and magnesium in its alloys. So that aluminum and magnesium have lower density when compared to their admixture. Since aluminum is 2.8 grams per cubic centimeter, the magnesium is 1.8 grams per cubic centimeter. By including low density materials, we can still able to reduce the density of composites. So that is the objective of the researchers. So here, most of the research that is up to usage of matrix material, 25% of matrix is used for aluminum and then magnesium. So here the synthesizing of magnesium is limited because it's very difficult to synthesize. When it reacts with during synthesization, when it reacts with oxygen, it forms oxides. So that It's very, and it is highly pyrophoric in nature. Okay, so because of that reason, so they have not won't go for magnesium matrix for, but researchers are by using the processing method, the researchers have concentration on finding magnesium matrix. Now, a lot of research papers are coming on based on magnesium matrix composites. So these were the type of reinforcements that are maximum used in nanocomposites, in ceramics, in case of boron carbide, silicon carbide, titan carbide, aluminum oxides, magnesium oxides, and tin oxides, yttrium oxides, zirconium, titanium borate, and zirconium borate. So based upon the size, so they can go for that. And also metallic, they go for aluminum, copper, molybdenum, nickel, and titanium, and others is carbon nanotubes. So these are the reinforcement which are mostly common usually for synthesizing nanocomposites. Sometimes they go for addition of two reinforcement hybrid composites. So on here, and in that they'll go for another reinforcement that is called the boron nitrate. So that's the density is very low, and sometimes they go for molybdenum disulfide graphite. So they act as a good solid lubricants, especially used for wear resistance properties and the corrosion to improve the corrosion resistance properties. Okay, so you need to so the type of, so I have given the type of reinforcement. So the reinforcement should for selecting the reinforcement, the following conditions should be satisfied. So for synthesizing nanocomposites, so this is a general thing. So it should increase in yield strength. The increase in yield strength and tensile strength at room temperature or elevated temperature while maintain ductility. Okay, so next one is increase of creep resistance at the elevated temperature, increases fatigue strength, improvement of thermal shock resistance, improvement of wear resistance, increases of the Young's modulus or reduction of coefficient of thermal expansion. So these are the things that we need to consider while selecting the nanoparticles for synthesizing nanocomposites. So here I have given, so aluminum matrix composites. As you all know that aluminum matrix composites are widely used for automobile and marine, transport industries, transport industries, and due to high strength to weight ratio, good gas stability and formability, high elastic and thermal conductivity. So here, and it is also known that the mechanical strength can be increased by using precipitate hardening. So here I given, so you are having, this is aluminum, and these are the major alloy elements that can added along with aluminum. From this we can extra aluminum, copper also, and so from this we can have different types of the is aluminum, zinc, magnesium, copper. So here these are the series, and it is means 99% of aluminum, copper, that is aluminum copper alloys, aluminum manganese alloys, aluminum silicon alloys, magnesium, aluminum magnesium alloys, and aluminum zinc alloys, and the lithium alloys. So this is a recent material that we are evaluating. So because since the density of lithium is very low when compared to that other reinforcements, but it is highly pyrophoric in nature. So these aluminum alloys are used in various industries, but we are concentrating in what marine application, that is superstructure, structural components, assembly nodes, components for assembly the mechanical functions, and especially in manufacture of ribs, hulls, all those things. So so there is a major drawback in this aluminum. So at aging temperature, the coherency between the precipitate and matrix lattice disappears due to the growth of reinforcing paints, and hence is losing hardening effect. So as a consequence, and the strength of the alloys has been decreased. So mostly go for 200 to 300 degrees centigrade. So in that case, we are go for so that inclusion of ceramic reinforced tends to increase that such properties. Okay, so next we'll go for. So here, so this is the research work that we have carried recently. So that synthesis of boron carbide and boron nitrate reinforced AL7075 hybrid composite using stirred methods. So here we have used the AL7075. So AL7075 has been selected as a matrix material. So due to its high strength, low density, low cost, and excellent castability. So AL7075 is used for transport and application, and wherever the wear properties and the corrosion properties has been increased, they can use it for this. We can use for these materials. And also we have used two reinforcements, boron carbide and boron nitrate. Since the density of composites of boron carbide and boron nitrate is very low when compared to that Al7075. So the density of boron carbide is 2.5 grams per cubic centimeter. The density of boron nitrate is 2.1 grams per cubic centimeter. Here we are using boron nitrate as a solid lubricant instead of graphites and instead of molybdenum disulfide. Because it is this boron nitride compared to the other reinforcements. And this boron nitride is exhibits lamellar crystalline structure with significant lubricating properties. In addition to that, they have the boron nitride have high thermal conductivity, low thermal expansion, superior shock resistance, and excellent excellent castability. So considering that, we have chosen boron carbide and boron nitrate. One is a hard reinforcement, another one is a solid lubricant. So this is the experimental methodology that we have found. That aluminum alloy Al7075 used as a matrix material, and there is a chemical compositions. So here we have used aluminum, the boron carbide and the reinforcement, that is boron carbide and boron nitrate as well. In that we have varied the percentage, 3%, 6%, and 9%, and we kept the boron nitrate 3% compounds. And the particle size of boron carbide and boron nitrate is less than 15 nanometer, which is commercially available from the market. That is from Sigma Altrich. We have found from that. We have obtained from that, and that is used as a reinforcement. So these are the processing methods methodology that were followed for synthesizing aluminum hybrid composites. So Al7075 alloy is melted in a resident heating furnace at 700 degrees centigrade. Since there is a presence of magnesium content in the alloy, so it should not be oxidized. So that we have gone for inert atmosphere environment. That is, we have supplied argon and SF gas at a minimum of 3.5 liters per milliliter. Since magnesium enhances the wettability of a matrix and reinforcement. So that should not be optimal. For that purpose, we have gone for a closed environment setup. So in order to have a homogeneous melt, the temperature of the melt is increased to 750 degrees centigrade. Then after that, the reinforcement particles are preheated to 350 degrees centigrade to remove the moistures present in the reinforcement particles, so that it also because of that we can able to avoid oxidation. And also we have increased the temperature of the melt to 850 degrees, to maximum limit. Since the temperature of the melting temperature of boron carbide is 1100 degrees centigrade, so that we have increased it to 850 degrees centigrade, and to obtain a fine grain, a fine interdirected pattern. And then we have we have added reinforcement of boron carbide 3%, 6%, 9%, and the constant of 3 weight% through external screw into the molten space. And the stirring speed and the stirring time has been maintained at a 600 rpm and 20 minutes respectively, in order to obtain the homogeneous distribution of reinforcement in the matrix melt. And finally, the die is preheated at 250 degrees centigrade, and then the molten slurry is poured into the die cavity, and it's allowed to cool at the room temperature itself. And finally, the cast samples are prepared as per ASTM standards. So these are the stir casting setup that we have used, and so these are the materials that we have performed as per ASTM standards. So we have two set of samples has been prepared. That is two tensile, compressive, hardness, corrosion, and wear resistance. So these are the performance measures. The optical microscope has been used to study the microstructures, and using scanning electron microscopes to use to find the distribution of reinforcement matrix and reinforcements. And Vickers micro hardness test has been used to study the hardness of composites, and the universal testing machine has been UTM is for to study the tensile and compressive strength of composites. And this is the soft spray test chamber that we use to find the corrosion properties of aluminum hybrid composites. Since we have these materials are mainly used for marine applications, as I told earlier. So because of that reason, we have gone for soft spray apparatus. So these were the testing parameters that we have maintained for corrosion resistance. That is 98% measured by hydrogram during the test, and the temperature of the test is maintained at 30 to 35 degrees centigrade. and pressure of air for atom. In that we have applied a salt, that is 5% of sodium chloride, 1% of magnesium chloride deionized water for 1 liter of solution. So for every few minutes we have it will spray automatically. So that by this is a sprayer. And so also here all the specimens were subject to cleaning with an aqueous solution, and which is not attacked the materials. The solvent cleaning was done only on the surface of the, sorry, it's aluminum, it's magnesium, I told. So these are the resultant performance. So these are the microstructure characterization of boron carbide and boron nitride reinforced aluminum hybrid composites. So here I have given that optical microscope has been used to study the microstructure of aluminum hybrid composites. The as-cast and etched samples are shown in the figure. So from the etching agents are shown in the figure, the etch and Keller reagent is used as a etching agent. From the microstructure, it has been shown the reinforcement particles are uniformly distributed throughout the matrix without indication of clusters. But in case of 6% of boron carbide, so we can be able to see some clusters around the regions of grain boundaries, aluminum grain boundaries. Okay, so it is clearly evident that at the increase in temperature of molten metal, the reinforcement particles cannot be dissolved to maximum, and hence it appears as a fine globular species in some regions of matrix alloy. So matrix alloy. So it appears as a, so the it is can be dissolved fully, so that it appears as a fine globular species in the matrix. And this can be also used as a good behavior in what compressive strength. It is also shows that the matrix aluminum shows a fine interdependent pattern of grains and are precipitated at the grain boundaries. Okay, so from the XRD analysis, it is clearly that strengthening mechanism occupies a important place of enhancing the mechanical behavior of aluminum hybrid composites. So here, the presence of boron carbide and boron nitride interacts with aluminum to form Al3BC, AlBl2, and AlNS interface reaction, and this is the strengthening mechanism which enhances the mechanical properties of synthesized composites. And still in that here, in that material, we are having Al and copper. So that the presence from the copper interacts with aluminum to form Al2Ce2. So that is mainly used for corrosion resistance. It has a barrier. So that is that it has not been found. So next we'll go for hardness of aluminum hybrid composites. So the hardness of hybrid composites is increased due to uniform distribution of reinforcements, matrix alloy, the presence of hard interface particles, and a large difference in thermal expansion between the matrix and reinforcements, which significantly increase the dislocation density in the microstructure of synthesized composites. So in addition to that, the inclusion of boron nitrate, that is a solid lubricant, also contributes on increasing the hardness of composites. It acts as a barrier along with boron carbide and inhibits the presence of dislocation during interdation. So that the hardness of aluminum hybrid composites has been significantly improved when compared with the monolithic material. Next, we go for tensile strength of aluminum hybrid composites. So it has been observed that the increase in reinforcement and the increase in ultimate tensile strength and reduction in percentage of elongation is reduced. So this is occurred due to the strengthening mechanism, adequate load transfer between the matrix and reinforcements, and Warren strengthening mechanism, and finally the grain refinement and dissimilarities among the thermal elastic performance of synthesized composites. So here the inclusion of secondary reinforcements exhibits heterogeneous nucleation sites, nucleation, and hence the further deformation of hybrid composite has been increased significantly. So the percentage of elongation is decreased due to increase in percentage of reinforcements. And due to the grain refinement achieved by hard ceramic reinforcement, and these tends to reduce the superplasticity effect, and hence the brittleness of the composite has been increased. So this is to be considered to be a major reason of due to percentage of elongation, reduction in percentage of elongations. So that is the thing I have here, inclusion of secondary heterogeneous elongation. And this is the compressive strength of aluminum hybrid composites. The compressive strength of aluminum hybrid composite has been significantly increased when compared to that monolithic letters, because the matrix reduces the turning moment of graining moment. So during staining, the inclusion of secondary reinforcements disintegrates the strain rate of hybrid composites, and and hence the fracture surface of hybrid composites appears to be smooth. Okay, so that it also found that it is also found that because of heterogeneous nucleation, the deformation of synthesized composites occurs at the grain boundaries, and it exhibits the plastic deformation which residues the nucleation of grain at the time of compressive loading. So you can able to see some of the grain refinement which are seen in that figure. So next we go for corrosion resistance. As you all know that aluminum alloys possess high affinity to oxygen, and it is treated as a reactive material. So the presence of copper interacts with aluminum to form AlCO2. So this acts as an obstacle for dislocation. So this phase performs as reduction of corrosion when the pH is increased. Owing to that disintegration of aluminum, the alloys through the surroundings acts as a cathode. So these can be overcome by adding suitable ceramic reinforcement or harder ceramic reinforcement. So in these cases, we have added the harder and stiffer reinforcement along the matrix alloys. So due to that, the corrosion properties of hybrid composites has been significantly increases. In another thing, the inclusion of secondary reinforcement acts as a heterogeneous nucleation, and it acts as a barrier of reduction in grain growth, and hence the grain size of the composite has been increased. So that is also important thing which is considered to be the increase of corrosion resistance of aluminum hybrid composites. So next we will go for wear properties of aluminum hybrid composites using boron carbide and boron nitride reinforcements. In that, pin on disc of wear testing machine as carried out under dry condition as per ASTM G99 and G990 posted. A sample size 6 mm diameter and 35 mm length steel material is used, and EN31 of surface roughness is of 0.3. So it is observed that the composites for all the combinations, that is by varying speed and varying loads, has significantly increased the wear rate, and it's also this is due to the fact that increase in load tends to increase the width of synthesized composites, and hence the wear rate also increases due to the presence of harder reinforcement, and this restricts the motion of dislocation properties, and hence the wear rates significantly increase when compared to the monolithic material. And so this is the friction coefficient. The friction coefficient for of each material has been increased. So the actually by using that formula, we have calculated the friction is 0.46 to 0.47 for hybrid composites. The coefficient of friction increases due to strengthening the effect of matrix and reinforcement, and also the dislocations in the alloys are the ineffective, which causes increase in hardness, the most important factor to enhance the wear resistance. Next, we'll go for worn surface morphology. So here, worn surface of all the specimens under variable load were covered with grooves parallel to the sliding direction and some plastic direction. So these grooves are associated with abrasive wears in which a hard asperities on the steel counterface in between the pin and is causing wear by the removal of material. So it is also observed that due to the presence of hard reinforced, the presence of adhesive wear is less, and hence the total depth deformation is smaller in hybrid composites. In addition to the grooving, some local plastic deformation and material smearing were observed. So are the same applied. So that's here we have got 3%, 4%. So here I given for only 10 Newton applied loads. So at the same applied one surface of 6% of boron carbide and 3% of boron nitride, composite is smoother and shows the fine grooves and limits plastic defacement. And in case of 9% of uranium, it is further improved. So it is observed that the enhancement of wear resistance is due to the improvement of load-bearing capacities of reinforcement particles, and the formation of transfer layer between the matrix and reinforcement will protect the surface from the abrasion. So it is also noted that when they increase the load from 10 to 13 Newton worn surface of synthesis, the composites gradually shows composites gradually shows less amount of adhesive wears, and it shows shallow scratches on the composites. So again, it is concluded that the worn surface of all the specimens under variable load were covered with grooves parallel to the sliding direction and some plastic. The inclusion of 3% of boron and 3% shows deep grooving. So when compared to that 6% and 9%, in grooving, some plastic deformation and materials have smearing, as I told earlier, and this is due to load-bearing capacity of reinforcement. The formation of transfer layer between the matrix and reinforcement protects the surface from the abrasion. So from this, it has been concluded that reinforcement particles are, from this, it has been concluded that is, and inclusion of boron carbide, the nano-sized particles, inclusion of boron carbide and boron nitrides are uniformly distributed in matter and found a few clusters around the regions of aluminum grain boundaries, and it forms the interfacial reaction as Al3B3, Al2B12, and ALEN. So this acts as a strengthening mechanism to enhance the mechanical properties of composites. And also, due to the presence of harder reinforcement, the matrix, the mechanical properties such as tensile strength, hardness, and the composite have been increased compared with the monolithic material. And the corrosion rate decreased by 18.5% between the 3% and 6% of boron carbide addition, whereas it decreased to 22.4% between 6 and 9% of boron carbide addition. So the wear mechanism of all the synthesis composites has been increased by varying loads, by varying different load and different speeds. So these were the conclusions that we have done, and these papers have published in the Journal of Material Research and Technology. So next we go for, so as I told you, next we'll go for being a light low density material. Then next we'll go for magnesium nanocomposites. So here we as well know that magnesium is a low density materials when compared to that aluminum. So there is 1.8 grams per cubic centimeter, and hence but the major drawback is it is difficult for synthesizing. So the research on magnesium material is exponentially increases because magnesium degrades naturally, and the Young's modulus is 40 gigahertz, similar to that of a human bone. So similar to that of human bone. So it is a hexagonally packed closed structure material. The strength is moderate and the poor formability, and strength is for but has poor formability. So being that used because of that, by adding suitable reinforcement, we can increase the mechanical properties of magnesium composites. And it is also known that the magnesium is very slight, that is 30% very lower than aluminum, and 73% lower than steel. So it exhibits good dimensional stability, machinability, and damping capacity. So the major drawback is low strength and poor ductility. So this has to be overcome. So by adding suitable nanoscale reinforcement in the matrix material. So here, so this is the introduction, as I told. So here we are using the performance of magnesium alloys has gained interest in recent years due to extent castability, machinability, electromagnetic sheathing, all those things. So here we have used titanium carbide as a reinforcement because since the density of titanium carbide is very high, that is 4.9 grams per cubic centimeter, but we need to increase the strength of magnesium composite. For that purpose, we have gone for titanium carbide. So titanium carbide have good strength when compared to other materials. So we have tried using titanium carbide as a reinforcement with reinforcement, and hence it have around 400 gigapascal as shear modulus and 188 gigapascal as the uh, sorry, the toughness is 400 gigapascal and shear modulus is 180 gigapascal, and hence the tensile strength and the compressive capacity is to maximum compared with pure magnesium. So for that consideration, we have used titanium carbide as a reinforcement. So here, this is the objective. The objective is to develop a titanium carbide reinforced magnesium nanocomposites by varying its weight percentage 3, 6, and 9% using powder metallurgy method for marine application, and to study its microstructure and mechanical properties of synthesized nanocomposites. So here we are using powder metallurgy proper. The reason for using powder metallurgy is so improved control volume fraction of reinforcement, uniform distribution of reinforcement, and improved control over the grain size and lower energy consumption during processing. So on consideration of nano level attempts, powder metallurgy is the process promising one the mechanical properties of magnesium improved by using dispersion hardening and stable particles of nano titanium carbide particles. So these were the need for the studies. So as I told you earlier, so it have low elastic modulus, low ductility, and low corrosion resistance, which enables the use of engineering application. To overcome this, we are adding a suitable nano reinforcement along with the materials. So these were the experimental methodology that we have done. So here we have used vacuum furnace setup along with argon for argon, along with argon. It is an inert atmosphere environment. When when it interacts with oxygen, it forms oxide, so that we can't be able to use for further. So for that purpose, the magnesium has to be synthesized only in inert atmosphere. So here, the present study, we have not used pure magnesium. We have used AZ91 magnesium alloy powder. So it is a die casting materials. It is aluminum zinc. That is aluminum is 9% and 1% of zinc, and that is AZ91. The mesh size of the powder is taken as 40 nanometer, and the titanium carbide is taken as 45 nanometer, which is available from Sigma Aldrich. So here we have maintained the compaction pressure has been maintained at 250 megapascal for 15 minutes at 250 degrees centigrade, followed by sintering process. So the sintering temperature has been maintained at 650 hours, and the sintering atmosphere has maintained 8 hours continuously. So that in order to get the material gets diffused. And from the during that, the atoms, the powder particles get diffused across the brain. So from that, the atoms in the powder particles diffuse across the boundaries of the particles, and hence a fusion of particles takes place, and creating one solid ball, which results in improvement in grain boundaries. So these are the so these are the samples that we have obtained. So this is a pure AZ91, and that is titanium carbide, 3% of titanium carbide, and 6% of titanium carbide, and 9% of titanium carbide. So these are the samples which we have obtained, and these samples has been sintered. These samples has been sintered, and so these are the result and discussion. The same performance that we have been using for my optical microscope as used to study the microstructure of magnesium nanocomposites, and Vickers micro harness has been used to study the harness of composites. So microstructures of titanium carbide reinforced magnesium composites. So magnesium powder has been so it has been observed the reinforcement particles has been uniformly distributed without indication of clusters. But here we can able to see that some clusters are found still by using the increase of percentage of reinforcement 6%. But we need to found so here we can able to see some particles of titanium carbide. So it cannot be, so it shows that it is not diffused into the material. So it appears as a fine powder induction composite materials. So from this microstructure, it has been observed that magnesium powder has been sintered effectively with the good fusion along with the formation of secondary phases. Fusion of primary magnesium powder leads to better bonding of composites. The matrix have secondary phase precipitated at the grain boundaries in addition to the following alloying elements, and also observed in the matrix alloys. So the grains present in the magnesium matrix appears as a lamellar structure. Okay, the grain present in the magnesium matrix appears as a lamellar structure. So there is the thing here. So the grain present in the magnesium appears as a fine lamellar structure, and thus significantly increase the mechanical properties of titanium carbide reinforced magnesium alloy composites. And it's also noted that due to the slip bands, it has blocked due to the presence of solutes in the grain boundaries, and the presence of titanium and the carbide phase acts as an obstacle that hinders the motion of dislocation and it is considered to be a significant factor to enhance the mechanical properties of developed composites. So these are the SEM and XRD images. So that in the XRD images, it clearly shows that the magnesium and titanium occupies the peak factors and enhancing the mechanical properties. So it is clearly evident the reinforcement particles are uniformly distributed in the magnesium matrix and ultimately such distribution encourages the bonding between the matrix and reinforcement. From the XRD analysis, it forms that. So it is also so that actually in the interfacial reaction when the magnesium have two into one is two principles, that is Mg17Al2 and Mg2Si. So that will act as a strengthening mechanism. But here in there MgTA2 yes acts is going to be as a strengthening mechanism. That is the interfacial reaction that we have considered. So from the from that interfacial reaction and due to the strengthening mechanism, the mechanical properties of titanium carbide reinforced nanocomposite has been increased significantly. So these are the hardness of magnesium nanocomposites. When compared, the Vickers micro hardness test has been improved. So it has been observed the reinforcement particles are uniformly distributed. Sorry, it has been observed that the hardness of magnesium nanocomposite has been increased with increase in the percentage of titanium carbide reinforcement when compared to the magnesium alloys. So this is due to addition of stiffer and stronger reinforcement, high density dislocation, and reduction in grain size. So the compressive strength. So the compressive strength of titanium carbide reinforced magnesium composites has been increased comparatively. Uh, has been increased comparatively with monolithic materials. So this is due to uniform distribution of reinforcement thematic alloy, reduction in grain size, transfer of load from matrix to reinforcement materials, and due to the strengthening mechanisms. So this acts as a strengthening mechanism. This acts as a barrier to reduce the dislocation density, and hence the grain size has been reduced. So due to that, the compressive strength of the synthesized composites has been increased. It is also noted. It is also noted that. Uh, it is all the interfacial reaction between the ceramic reinforcement and matrix metal can generally improve by wetting and bonding between them. So during compression, so it has been found that some brittle fractures are raised in the materials. So and also is that the micro cracks are gradually generated, and then it is propagated in the AZ99 matrix throughout the interface between the ceramic and the ceramic reinforcement particles and the matrix. So these were the same images that we were. So it's seen that still the titanium carbide particles are able to see in that same images. So it is also not have completely dissolved. So it appears as a fine globular species in the matrix material. So sometimes it is also, we can also tell that due to cushioning effect, it is able to withstand the load, and hence the compressive strength also increased. So this is the corrosion resistance of titanium carbide reinforced magnesium composites. So the corrosion rate of AZ92 magnesium alloy depends on alpha magnesium phase and its composition, since it possesses corrosion rate higher than the beta phase. Okay, the beta phase. The second phase acts as a micro cathode. So that Mg17Al2 and Mg2Si. The second phase acts as a micro cathode with respect to that alpha magnesium anode, forming microscale galvanic cell, which reduces the corrosion rate of alpha magnesium solutions. So this is due to the fact that the inclusion of hard ceramic acts as obstacles, and it prevents oxidation. So that is a major reason for improving the corrosion resistance. So these are the conclusions that we have obtained. That is microstructural characterization of titanium. So the titanium carbide has reinforced. The titanium carbide particles are reinforced effectively, and it forms a homogeneous distribution of matrix through is homogeneous distributed through the matrix. So on compressive loading, the addition of 3%, 6%, and 99% titanium has lead to increase restricts the plastic flow in the matrix alloy. So that is a basic reason for increasing the compressive strength of composites. The other thing is the hardness and here I have not showed the wear resistance. The hardness and wear resistance of titanium carbon reinforced composites have been found higher compared with the as-cast AZ91 alloys. So and hence the corrosion resistance has been simply significantly increased due to inclusion of hard ceramic reinforcement, since it acts as obstacle and prevent oxidation at elevated temperature. So next we have gone for synthesis and characterization of synthesis and characterization of nano glass particles reinforced AZ91D magnesium alloy composites using solid phase methods. So here the objective is to develop nano glass particles reinforced magnesium composites by using weight percentage of 4, 8, 12% using powder metallurgy for marine applications. So in that, so it's a nano glass particles. So nano glass particles simply is called borosilicate powders. That is commercially available from 3M. So that is the reinforcement that have used, and it studies microstructural and mechanical properties of synthesized nano composites. And so these are the experimental methodologies that we have used. So selection of matrix and reinforcements, and the matrix and alloy and the nano glass particles are the two essential constituents of synthesizing magnesium nanocomposites in the present study. So since we have used AZ91, that is due to high strength to weight ratio, good ductility, better damping characteristics, excellent castability, and good corrosion resistance. So considering that AZ91D alloy has been used. And so after that, fly has synospheres, that is so in that nano glass particles, like we have different types of reinforcement. The fly asinospheres, nano glass particles is a porous. It seems to be hollow, micron level. Nano glass particles and metals and engineering ceramic microspheres. All those things can be used as a reinforcement in the case of water. So the thing is, we can able to create a porosity in that material also. So, but that is from that we can able to obtain metal forms in that material. So here these are the chemical constituents of nano glass particles. That's SiO2 and B2O3, calcium oxide, magnesium oxide, and Na+ that are commercially available from 3M Technologies. So this is the thing that we have used. This is the matrix. A is 91D as used as a matrix material. So this is the same image of that nano glass particles. So that's so these are chemical compositions. So that is A is 91, aluminum 8.3%, manganese 0.13%, zinc 0.35%, and we have this the XRD images of that ETEX. This is the same image of nano glass particles, and a resource for single nanoparticles. This seems for globular structure, and maybe you can use it for create. This material can also use to create a metallic foams. That is porosity can be incorporated by using these reinforcements. Okay, so there is a
sir, excuse me, sir.
Thing.
Sorry to disturb you, sir.
So here,
excuse me, sir.
that this is the processing methodology that we have done. So that A is that magnesium alloy is powder is mixed. Yes.
Yes. Sir, you are going a little bit.
Hello.
Little bit fast,
yes,
sir.
Tell me, sir.
Yes, sir. Yes, sir. Can you reduce your speed?
Hello.
Sir, is it
Hello?
audible, sir? Is it audible, sir? Sir, is it audible, sir?
Okay. I will try to maintain this. Okay.
Okay, sir. Thank you.
Yeah, I'm audible. Right now. Yes, sir. Hello. Yes, sir.
Yes, sir.
Okay, sir. So this is the processing. Hello. This is the processing method. So that's A is at 91D magnesium alloy powder is mixed with the nano particles by varying weight percentage. So since here the mixing of nanoparticles with A is at 9 to magnesium is very difficult. For that, a set of several setup has to be needed. We need a uniform to obtain uniform distribution. We need a fan-like type stirrer. So that we have kept the material into the bowl, and then we can by using effective stir can we can able to attain the that we can able to attain that material homogeneous distribution. So that is the thing. So from that only we have created that powder. So then the metal is compacted. Then the metal is compacted. And so the die for compaction is designed, and it is the EN24 alloy is used for used as a die. So the die for compaction design and the fabrication using EN24 such as compacted specimen the dimension of 30 diameter and 20 height. Okay, so it is subjected to warm compacting. So that the atoms, the atoms, that gets diffused. So that will go for warm compaction, and hence, due to warm compaction, the reinforcement particles can able to hold with the matrix materials. So here I have used the compaction pressure as the compact 350 megapascal. The warm compacted temperature is 150 degrees centigrade. So this is the sample that we have obtained. And here we have done experiment in two furnaces. One is tube furnace and another is a vacuum furnace. So these are available in Anna University. So here, after compaction, the materials are subjected to screen sintering. Okay, so here the sintering has been carried out in tube furnace and two furnaces, that is tube furnace and the vacuum furnace. So here, to prevent oxidation. So as I told earlier, magnesium is prone to oxidation when it prone to oxidation when it is at the open temperature. So for that we need a closed environment. So that we have sent. So this is the thing. So we have sent we have kept the material inside this tube furnace, and from that we have sent that to prevent so to maintain inert atmosphere, we've sent argon gas into that. Okay, so from that we can able to prevent oxidation. So the argon gas flow is arranged with a bubbler unit to monitor the argon flow. So normally 3 to 0.5 liters per minute has been commonly uh, used, because sometimes in argon gas also there may be some little amount of oxygen will be present. So that is also causes to material to be oxidized. So for that purpose, mostly we go for 3.5. So nowadays they are using SFCs and CO2 as a inert gas atmosphere. Instead of argon, they are go for CO2 gas. So here, so three trials were made with the tubular furnace and the vacuum furnace. So in that and tubular furnace, first we have gone for 400 degrees centigrade, and we have gone after that we have in each trial, air evacuation followed by argon purging is carried out, and the process is repeated at regular intervals while raising the temperature. Okay, so in every trial, the specimen was first heated to 250 degree for 30 minutes. This is specimen for degassing the compacts. So we have made three trials: 400, 500, and 450. And also in similar to that, we have increased the temperature to 550 degrees, 600 degree, and 650 degrees centigrade. So in order to get the homogeneous mesh, and you have to improve the sintering quality of the material. Okay, so what are the problems that we have identified in solid phase materials? It was found that there will be some only the thing is the sintering temperature has been the quality of sintering has been completely increased when compared to tubular furnace over vacuum furnace. So it was found that it was found that the outcome of experiment carried out in the furnace setup is different. The tubular furnace surface is different than the vacuum furnace. So residue is obtained from the tubular furnace. So at 400 degrees centigrade with the soaking time, but the sintering quality was slightly improved when compared to that 400 degrees centigrade. And if we try to increase the temperature to 500 degrees centigrade, the temperature tends to burn. So that is the major drawback that is. So these things. So we have seen that. So we have considered that due to that less amount of temperature, so that it may be happen. So that we have try to increase the temperature, and we have tried to go for another setup, vacuum furnace setup. So in that we have you first gone for, so increase the temperature from first level 400 to 500 level. In vacuum furnace setup, same result were observed, but the sintering temperature was increased to 550 degrees centigrade, which could not be achieved in tubular furnace. Okay, so first trial we have increased to 400 degrees centigrade. At the same time, in vacuum furnace, we increased the temperature. But only the sintering temperature, sintering quality has been improved. And again, we have gone for 550 degrees centigrade with the soaking time 1 hour. The specimen showed cracks which were similar to that made of using.
I request all the participants, due to some network problem, our resource person has missed the presentation. Please wait. We will contact our resource person.
Sir, assessment link.
Dear participants, please wait. We are trying to contact our resource person. Due to network problem, he is feeling he can't unable to join meeting. He will join within 5 minutes. Please wait. Participants, please wait. We have contacted our resource person. He will join within a few minutes. Sir, your presentation is visible, sir. Sir, we can't hear your voice, sir. Participants, please wait. Our resource person is having some network problem. He will join again within few minutes.
Sir, audible now?
Sir, it is audible, sir. Audible, sir. Yes,
Okay, okay. Thank you, sir.
yes, sir.
Shall I share, sir?
Yes, sir. Please share your screen, sir.
Yes. Actually, solid phase method, nanoglass particles reinforce the solid phase, right?
Yes, sir. Yes, sir. That portion.
So this is the thing. Okay.
Yes, sir. Just you are continuing, sir. From here onwards, you are continuing, sir.
Could you able to,
Yes, sir.
see the screen over there, sir?
Yes, sir. Screen it is okay, sir. But yes, sir. Perfect, sir. Perfect. We can proceed, sir.
Shall I proceed, sir?
Yes, sir. Please, sir. Please.
So next we have gone for synthesis and characterization from nanoglass reinforced the AZ920 magnesium alloy composite using solid phase method. So this is a thing that we have used for marine application, especially for buoyancy application. So here the nano glass particles are borosilicate glass that were commercially available from 3M technology that have been used. So here, first we have gone for powder metallurgy methods. So in that the objective is to develop nano glass particles reinforced magnesium composites by varying its weight percentage, that is 4, 8, 12% using powder metallurgy method for marine application, and to study its microstructure and mechanical properties of synthesized composites. So 920 as a matrix material, and so here is a 920 deep high strength to weight ratio, good ductility, better damping capacity, excellent cast stability, and good corrosion resistance. So based upon these factors, we have chosen AZ 920 as a matrix material. And also we have chosen the reinforcement as a nano glass particles. It simply seems to be nano hollow particles. Some researchers are going for finding of for using for developing metal foams, they'll use these hollow spheres like that. Okay, so the composition of nano glass particles are made of SiO2, B2O3, calcium oxide, magnesium oxide, and the sodium salts. So that are the composition of nano glass. So it's a borosilicate glass, that is simply called borosilicate. The hardness of this borosilicate glass is very high when compared to the other reinforcements. So considering that, and hence the corrosion property is very high when compared to that other reinforcement. So because of that reason, so this is considered to be a major thing for consider this as a reinforcement. So here I have given the chemical composition of AZ 91D magnesium alloy powder. So these are the chemical compositions, and this is a borosilicate glass powders. So this is the nano glass particles, and we have took one. So, and from that we have took a single reinforced, and these are the ERACs that we have obtained from that reinforcement particles. So here we have blended the reinforcement particles with magnesium alloy powders by varying its weight percentage. So for blending, so it is a borosilicate glass, so the wettability will be very poor. So that we need to have uniform distribution throughout that matrix. But for in this powder matrix, we need to create before itself. So we took a bowl, and by using the fan like a stirrer, we have placed a reinforcement and matrix and was stirred well, and from this we obtained this composite powder, and we have used EN24 as a die with dimensions of 30 mm diameter and 20 mm. And after that, green compaction. After that, sintering has been temperature. So before that, we have compacted the green. Warm compaction has been carried out to 150 degrees centigrade at 350 megapascal. So because we have not increased the compaction pressure over here, since it's a borosilicate, it should not be broken, or it should not be tend to deform or something due to that warm compaction. So that we have given 350 megapascals. So here in that we have used two furnaces for sintering of nano glass particles, reinforced magnesium composites. So one is tube furnace and the vacuum furnace. So these are available on NIST. So in that the green compact is subjected to sintering process. So here to prevent oxidation and excess burning, we are sending organ gas through it. Okay, so in order to prevent oxidation and excess. So this is the setup that we are using, and we are having that bubbler unit to control the pressure of that liquid flow into that. So this is a tubular furnace, so just like a boat-like structure. So we're going to keep a material in that, and we are getting and we are sending argon gas into that material. So that is a tubular furnace, and next we have vacuum furnace. So this is the thing. So inside that material we are going to keep that. So we are going to we are having an argon atmosphere in a closed environment. So here we have sent 3 to 5 liters per minute of argon. So from the literature we have taken that 3 to 5 liters per minute. So nowadays they are using CO2 instead of argon. They go for CO2 as a inert gas atmosphere, because there may be some oxygen present in that, so that is also cause the material to oxidize. So instead of that, they are going for CO2. Okay, here three trials has been carried out. So each and every trial has been carried out on different temperature. One is tubular furnace and vacuum furnace. And tubular furnace, first we have gone for 400 degrees centigrade, and next we have gone for 450 degrees centigrade, and the next finally we go for 500 degrees centigrade. And in vacuum furnace, we have increased the temperature to 550 degrees centigrade, 600 degrees centigrade, so 650 degrees centigrade. The reason is we have not obtained the composite properly. So for that purpose, we have increased the temperature to 550 degrees centigrade. So in the before going to each trial, air evacuation followed by organ purging is carried out, and the process is repeated equal interval of time. Okay, so first problems identified in solid phase methods. So from the outcome of the experiment, we have identified. So identify the effect of sintering process. Okay, so in a tubular furnace at 400 degrees centigrade with the soaking time 1 hour, the specimen showed some signs of cracks developed on the side walls. Okay, so due to the escape of volatile matters or due to poor wettability, it forms a cracks on the surface of the material. So that we have decided to increase the temperature to 450 degrees centigrade, but the soaking time has been maintained 1 hour respectively. So also, by increasing the temperature for 400 to 450 degrees centigrade, it shows same cracks on the surface of the material. So then we have decided to go for 500 degrees centigrade. So when still you increase the temperature 450 to 550, so the material starts to burning, so that we can't be able to get the composite. So that is the thing that we obtained in the tubular furnace setup. So after that, we have decided to go for vacuum furnace, and we have decided. So if we increase the temperature, so what will happen? That is the thing that we have thought of, and we have gone for that. And in vacuum furnace setups, we have increased to 550 degrees centigrade. So the soaking time has been maintained as 1 hour. So it shows same crack which are similar to that of made of tubular furnace. So as the temperature was increased to 650 degrees, the specimen starts to burn. So this is the thing that we have obtained. The only thing is we can increase the sintering temperature. So it is in fact the crack development was due to escape of volatile temperature, but the specimen was subjected to SIM analysis. So here we can able to see that the nanoparticles are appears. It is not burnt. So due to escape of volatile matters, and it gets oxidized, so that we can't able to get the composite. That is the thing that we have observed from that research. So it is also observed that in the sintering process, the thermal energy from the external source is transferred from the outer source to the inner by conduction, and the penetration of infrared radiation is very small, and the heat energy distribution is limited to the outer surface. So due to that process also, the materials cannot be, the composite cannot be sintered. So these result, the core material have lower temperature than the surface of the metal, hence the poor absorb into the matrix and hence the material cannot be sintered. So that is the reason that we have found in powder metallurgy method. So then we have decided to go for liquid metallurgy method. So in that liquid metallurgy method, we have different types of things. So this vacuum die casting, Swiss casting, stir casting, so centrifugal casting, like that. So due to the availability, we have decided to go for stir casting. So it can be used for fabrication, and we can obtain homogeneous distribution by using effective stirring, all those things. So consideration, we have gone for stir casting support. So that is the synthesis and characterization of nanoglass particles reinforced alloy composites using liquid metallurgy. So this is the stir casting. So based upon this, we have gone for synthesizing of a nanocomposite by using stir casting methods. So this is the schematic diagram that I have given. So that the setup that we have used is bottom pouring. So to minimize the interaction between the matrix and to minimize the interaction between the atmosphere and the molten bed. So if it gets so that it might not be oxidized. So here we have placed the AZ in magnesium, so that is that is gas powders AZ91 in that material, and it is melted. So it is called nanospheres or hollow glass micros. Sometimes it will tell that. So in that glass spheres, it seems to be hollow sometimes. So that's sometimes we go for hollow glass particles, nano glass particles, and the metal is melted in a resistance heating furnace. And the stirring speed was maintained at 200 rpm to ensure the molten metal was melted. So the metal is not melted. Then we have increased the temperature to 700 degrees centigrade, and the stirring speed was increased to 300 rpm. 300 rpm. 300 rpm. So still that after that the nanoparticles are preheated at 450 degrees centigrade in order to remove the moistures and gases present in the surface of the reinforcement particles. So after that, the various weight percentage of reinforcement particles are added manually into the melt. The stirring temperature was increased to 700. Stirring speed was increased to 400 degrees centigrade, and it was maintained at 5 minutes. And finally, the molten slurry is poured into the die cavity. The die is coated with sulfur to prevent oxidation, and it is placed near the bottom of the screws to minimize the interaction between the molten composites and the atmosphere during gravity pouring. So these are the things that we observed by seeing the microstructures. Clustering of nano glass reinforcement particles has been observed in the microstructure at a stirring speed of 400 rpm, stirring time 5 minutes, and a temperature of 700 degrees centigrade. So the presence of cluster is due to surface tension effect. So it was decided to increase the process parameters, the stirring speed, stirring time, and temperature, all those things. So the stirring speed was increased to, stirring speed was increased to 500 rpm, and the stirring time was maintained at 10 minutes. So that again the reinforcement particles are found clustered in some region. And finally, so apart from the so it is also noted that apart from the stirring, the temperature and the mass fraction are also considered to be important to avoid clustering. So in that, the interface particle distance increased by increasing the speed of the procedure. So from that, it is identified. So we have increased the temperature to a maximum of 600 rpm and made it 15 minutes stirring time. And the temperature of the melt has increased to 750 degrees centigrade, and it is and it was casted. So from that, it is obtained a maximum amount of uniform distribution of reinforcement particles obtained in the matrix alloy. So these are the things, and these are the same images of there's nanoparticles, glass nanoparticles, or sometimes hollow glass particles. So these are the microstructure of magnesium nanocomposites, and still we have found some porosity and on the surface of the so this is as-cast and HD samples. On the surface of the metal we have seen some porosities, and we have seen, and by through cross section we have seen the nanoparticles into it. So this is the 4% of nanoglass particles reinforced magnesium composites, and this is the 8% of nanoglass particles reinforcers. So here the etchant picrol is used as a etching agent, and so this is the 12% of nanoglass particles. So that increase in the percentage of so the more amount of surface porosity is obtained in that material in as-cast samples. So that is the thing that is also needed. So but need to be avoidable. So because of this, the machinability properties cannot be carried out. So things need to consider on the improving the surface properties. So that is another area in this research work. So from that microstructures, it has been observed that reinforcement particles are uniformly distributed through the cross section. So it has been noted that grain boundaries of magnesium matrix are enclosed with the nanoglass particles and was uniformly distributed. And we have seen some marginal deformation of glass particles. So here, due to heat, that is, it can't be dissolved. So the marginal deformation of nano glass particles may be probably due to heat input. However, the majority of nanoparticles have retained the shape of spheres as shown in the same image. So that is a thing. So some glass particles tends to, yes, so that glass particles tend to dissolve interacts with magnesium to form Mg2SH because the presence of borosilicate in it. So that will enhance the mechanical properties, especially compressive strength of a composite. So it is also noted that the higher concentration of reinforcement particles in the melt, seem to have lower rate of cooling, resulting in reduction in the dendrite pattern of solidification. So here we have found that the precipitates of Mg17 Am12 as a UTT precipitates that are found along the grain boundaries of magnesium solid solution. So the interfacial reaction plays an important role in strengthening the composites, as I told you earlier. So with the presence of borosilicate, it interacts with the magnesium to form Mg17Al2 and Mg2Si. So this Mg2Si acts as a strengthening mechanism to enhance the compressive strength of nanocomposites. So the presence of is also these particles are the present, and also notes the presence of stable at elevated temperature, therefore preventing slide of grain boundaries. And this presence of Mg2 acts as a nucleation pod in the melt with a significant alloy. So it's just nano hollow particles. So that's uniform pore size has to be maintained. And we go for influence of nano-sized glass reinforcement and tensile strength. ASTM, as per ASTM standard, it has been observed. It has been when the composite has been performed. So it has been observed that the ultimate tensile strength of magnesium nanocomposite with the dissimilar mass percentage decreased compared with the AZ91 magnesium alloy. So it's not increased; it has been decreased. So here, the reduction in strength originates weak adhesion among the ceramic particles between the matrix and the reinforcement particles. So hence it necessitates the load transfer from matrix to reinforcement particulates, and hence the yielding of magnesium nanocomposites behaviors contains defects. So that process, so that thing, the properties tends to increase significantly. So it is also observed that the tensile strength of magnesium nanocomposites has not been ensured due to variation in grain size of reinforcements observed in the nanocomposites. And since the HCB crystal of magnesium alloys deformity is the deformity of is limited, and hence a lack of addict slip activity, and even though the particle size of reinforcement added in the matrix alloy is nano length. So and also there is no premature failure has been observed in the magnesium composites observed in the composites. So actually that's compressive strength of the nano-sized reinforced composites. In that, as per ASTM E9 standards, the compressive strength has been performed. It has been observed that the compressive strength of magnesium nanocomposite is higher than the of as-cast magnesium alloy. The compressive strength of magnesium can be increased due to increase in mass fraction of the reinforcement and in matrix alloy. As I told you in this case, the presence of Mg2SA interface with the matrix and interface increase the mechanical properties, and it shows here typically a linear region and a plateau region and densification region that materials the stress strain curve. So as I say, it is similar to foams, metal foams, that is the stress remains constant up to that elastic limit. After that, it is densification strain. The strain that is called linear region, densification region. So in linear region, the compressive strength of nanocomposites deformed linearly, and then plastically followed by a drop in stress entered into the plateau region. This plateau region, the stress remains constant. It can be able to withstand the load from matrix to the reinforcement. So finally, the nanoglass particles tends to break to this maximum strength which is present in that, and from that the stress, and due to that it remains the stress level remains constant, and it appears as a flat and stable with increases the slope. And finally, the densification strain depends upon the level of porosity entered in the nanocomposites. So it is similar to that. So during compression testing, the compression material fills up. So sometimes there will be some matrix porosity absorbed in that material, as I showed in that microstructure. So that can also be filled during the compression material. That is, the matrix material fills up the matrix porosity. So woven into the nanoglass particles tends to fracture, and the matrix porosity embedded within them is disclosed. So that is the matrix porosity also disclosed by due to the compressing. So and thus occupies compressing the material. So this causes the enhancement of compressive properties of nanocomposites. So here, the nano-sized glass particle reinforced magnesium composites have been fabricated by stir casting process from the microstructure state characterization, and the tensile and compressive stress has been it has been observed that the tensile strength has been is very reduced, and also the compressive strength has been increased. The decrease in compressive strength is due to weak adhesion among the seminal particles, the matrix, and the reinforcement particles. And these were the references that I have chosen for this STP. And thank you all.
Sir, thank you, sir. Thank you very much,
Thank
sir.
you.
So, shall we go with the question and answer session, sir?
Yes, sir, you can ask.
Yes. Now I request our participants, please unmute yourself. You can ask directly to our resource person, or you can type your question in the chat box. We will ask on behalf of you. I request once again, participants, please unmute yourself and you can ask a question. Happy to our resource person. Sir, we are having one question from chat box, sir. Shall I read it, sir?
Yeah. Yes, sir. Yes, you can.
This is from Professor Rajesh. Excellent presentation,
Yes.
sir. What made you to choose the percentage of reinforcement, 3%, 4%, 9%, etc., for addition into base metals? Is there any specific reason, sir?
Yeah, actually, the thing is for polymer batteries composites, they mostly go for maximum of 5%. So in this case, we can so particle agglomeration has been occurred in the polymer matrix composites. The same thing can be used in metal matrix composites, but we can increase the percentage of reinforcement. If you go for low percentage, means it will go for residues. So that and the density of the total amount of material is also very high. So that for that, based upon that, we are choosing as most 3%, 6%, and 9%, and maximum they'll go for 12%. For 9% itself, we have seen particle agglomeration. So that is the thing. So if we go for minimum percentage, so there will not be any significant changes occurs in that material. So considering that, we have kept a constant of 3%, 6%, and 9% as cited in the literature.
Thank you, sir. This is another question from Sunil Kumar Chaudhary. How the Young's modulus of metal matrix nanocomposite will increase since it is a basic mechanical property?
Yes, I told you earlier. So Young's metal is depends upon the strengthening mechanisms. Using Goravan theory mechanism, enhanced density location, load bearing capacity, and in kinds of nanoscale mechanism, as I told you earlier, by using C mechanism, K mechanism. So that I told you is critical flaw size reduced by added new nano reinforcement materials in the nano reinforcement particles in the matrix material, and the K mechanism, as I told you, fracture toughness is increased, relates to arc curve. So there is resistance to fracture versus crack orientation. So from this, we can able to identify that.
Okay, sir. Sir, another question from Sunil Kumar. Yes, sir. Yes, sir. Another question from Sunil Kumar Chaudhary, sir. What is the process of mixing the nanoparticles in stir casting?
So the process of mixing is similar to the conventional material particle, but we need to preheat the reinforcement particle to a maximum of 350 degrees centigrade, so that in the moistures which are present in this can be removed, and it is usually used for used to improve the wettability. So that is the thing. So once the molten metal is full melted completely, so after 5 minutes or 10 minutes, then we can add it to. So actually they go for 10 minutes in literature solidification. So in that we have an equation, Arrhenius equation, at which time we need to incorporate the reinforcement. You just go through that Arrhenius equation. So that from that we can able to identify the viscosity of the metal. So that at that time, from that derivation we can able to identify at which time we can able to all those things, add this reinforcement in these things.
Thank you, sir. I request participants, please unmute yourself and you can ask questions directly to our resource person, or you can your question in the chat box. Sir, it seems no questions, sir. Shall I proceed with vote of thanks, sir?
Yeah, okay. Before that, I have to tell one thing to that. So nowadays, they are concentrating on polymer metal matrix composites and polymer metal matrix nanocomposites. Actually, they are using polymer as a base matrix, and to enhance the mechanical properties of that, they're using nano-sized metal powders as a reinforcement, and they're and adding 2 to 3% maximum because the viscosity of the polymer is very high. So instead of natural fibers, all those things they're using was polymer metal matrix composite. That is the recent scenario that is going in case of nano composites. But in case of metal nanocomposites, especially in polymer, especially in the field of marine applications, so this polymer matrix. So that I ask the participants, those who are doing research, try to do in that, and those who are need to choose a new area, you try to choose for that. So it is another thing is mostly go for magnesium matrix. So this is a eco-friendly, it is a biodegradable material. So that's a large vast of areas are available in the magnesium. The only drawback is we need to have processing difficulties that we need to minimize. Nowadays it is become easier. So everywhere we are having that setups. Every IITs, NITs, and NIST we are having that setups. I think JNT may also have that. So mostly go for magnesium matrix. So magnesium is very highly for compressive molding when compared to that aluminum, all those things. So the weight reduction occupies the significant reduction in low density materials. So mostly I'll prefer for the new researchers to go for magnesium matrix nanocomposites. And thank you.
Sir, few questions are in the chat box, sir. Shall I proceed, sir?
Okay, I'm waiting for that.
Thank you, sir. This is a question from Professor Ravi Kumar. Sir, can you suggest the better paths of nanocomposite for better heat transfer application?
So for better transfer means for I want to know what is the application he's going to be used.
Actually, he's telling a heat transfer application, sir, but not specific. He didn't mention anything specific.
So for heat transfer, yes.
Sir,
hello?
For heat transfer, this is Ravi Kumar, sir.
Yes, sir. Good morning, sir.
For the enhancement of the heat transfer rate, sir. So which kind of the nano composites is preferable? It may be metal matrix or polymer matrix or ceramic matrix, sir. That is my question.
Okay, if, as I told you earlier, polymer matrix cannot be used for high gradient temperature, but it can be used but for that, instead of that, metal matrix nanocomposites are only used for high temperature gradient purpose. In that, what application you are going for? That is the thing, because if you go for reduction in density means you need to choose the reinforcement density very lower, so that you can maintain the density of the composite. So that is the thing I'm asking. So thermal expansion, each and every ceramic they have coefficient of thermal expansion, and especially in titanium carbide, the melting point and the boron carbide, all those things. And since we have on paper that is boron nitrate, also they are using the good. It's a solid lubricant, but it is also used as the high thermal reinforcement.
In a heat exchanger, sir. In heat exchanger.
In heat exchanger, you want heat exchanger. Heat exchanger means. Hello.
Yes, sir. In case of the heat exchangers, which kind of the hybrid component is preferable in order to enhancement of the heat transfer rate and as well as to reduce the pressure drops?
Actually, go for boron carbide groups. So that the density is very high. So that the density is very low. That is 2.4 grams per cubic centimeter. And what is the matrix that you are going to use?
That one, no idea, sir.
So okay, you go for AL 7075 plus boron carbide and nano-sized boron carbide, and also go for a few percentage of titanium carbide, keep as constant. Okay, that is 1% keep as constant. So this is the thing that you use for that. So these are the two reinforcements that can able to withstand high heat resistance. So and another thing is AL7075 is a thermomechanical treatment process, so that you can use this material further.
Sir. Thank you, sir.
Okay.
Thank you. Any doubt?
Okay,
Shall I contact you, sir? Any doubt regarding to this case?
you contact my lady.
Sir, thank you, sir. Thanks a lot,
So
sir.
another thing is another thing is go for the standard reinforcement, sigma Aldrich or biocorpuscles. So I have seen some of the papers. The reinforcement particles have good properties. When they added with matrix material, it should not improve that. So that because of that, poor quality of reinforcement. So go for standard reinforcement. The cost is very high, but based upon that application, you need to go. There is no other way.
Sir, thank you, sir. Thanks a
Okay,
lot.
sir. Thank you. Thank you very much, sir.
Thank you, sir. This is another question from Professor Narendra Mohan. Aluminum, magnesium, other than any material, sir, for PMMC?
Actually, now they are going for zinc-based material. Okay, so actually they have go for intermetallics, aluminum, zinc, magnesium composites, aluminum, magnesium, copper composites, like that. So that the percentage of intermetallics are added based upon the applications. So from that you can create an alloy and you can use this.
Thank you, sir. Sir, now,
Magnesium. Yes.
sir,
Hello.
Professor Pradeep, sir, please go ahead.
Hello.
Yes, sir, please, sir.
So
Very good afternoon.
can you
Sir.
hear me?
Good afternoon, sir. Yeah, I'm here.
Yeah,
I'm here, sir.
I'm Dr. Pradeep from Muscat.
Yes.
So even my area is also in the mathematics composite. So,
Yes, sir.
you have added nearly about 12% of reinforcement in the matrix, right?
When I have used 4, 8, and 12% for magnesium, and the 3, 6, and 9% reinforcement for aluminum.
Okay, by using a normal stochastic, gravity pouring stochastic furnaces,
Yeah,
right?
normal is a gravity pouring test with a closed environment setup.
But which one you have identified the better qualities of? Which percentage of reinforcement?
And 9% of reinforcement.
Okay. So which method you have adopted? The reason why we have conducted nearly more than 40, the castings. But when we
Yes.
had more than 5% of the reinforcement, the wettability is not really happening. That means the matrix is
Okay.
not really in contact with the reinforcements. The reinforcement, it's like
Actually,
remains
did you
over
use
there
any
in the crucible.
salts in that?
It crucibles as a completely like an ash. Okay, so it's not mixing properly. If we increase more than
Sorry.
5%, so even we have
Okay.
done ultrasonic stirring and all that. But in your case,
Okay.
we are using just a normal stir casting process, and you are mentioning that 9% is getting a better quality.
Actually, I want to ask you
extent.
whether you're using conventional stir casting or bottom pouring type with a closed environment.
No, we are using both stir casting with squeeze.
I'm not asking for sarcastic. We are having a closed environment setup. Since I am using AL7075, that magnesium is present in that. So that we are using closed environment. So in order to prevent
closed
oxidation, closed environment. So you can able that. So because of that reason, if you go for open, so it gets oxidized. So that you can't be able to get. So go for closed environment setup, sir.
And I've gone through many papers that they have used. They are using some degasser and all that to reduce the porosity. So even we have tried that, but it's not giving a proper result. So according to you, it's better to go for a closed environment.
Yeah, go for closed environment because in alloys mostly they go for they add some percentage of even in pure aluminum casting will add some magnesium to improve the wettability between the matrix and reinforcement. In conventional they used some salts, colon salts, all those things to enhance the wettability. Now that things and all they have upgraded, so we can use for closed environment. Instead of that, you send carbon dioxide and SF6 as yeah. Supporting gas, protecting gas. The thing you have get ash is the thing what you have get ash is it's get oxidized. Okay,
Yeah,
so
yeah,
that
that's true.
is the
So
other
that's
thing.
true.
Yes,
That's the
sir.
reason why we have tried with the vacuumizer and all that. But anyhow, whatever we
Yes.
have tried more than 40 castings, but we we could not add more than a 5% of the reinforcement. So anyhow, as we will try
So
with, as
okay,
you
if you
suggested, 5%.
I can able to do help for you, so that you set the so what do you tell the reinforcement and matrix, so that I'll put casting in my office in my college, and I will send to you if possible. I need it. I can do that help for you.
Okay, sure. I will mail you. Thank
I
you.
will mail you. I will be touch with you. No problem.
Okay, thank you.
Thank you, sir.
Thank you, sir. This is another question from Professor Sarath. Sir, how about
Yes.
graphene-based composites?
However,
How about graphene-based composites? I think this is the question, previous question continuation, I think, sir. That means what are the other materials we can use in the PMMC like that? As you know, I think so.
yes. What has to do?
Sarath, Professor Sarath, sir, can you unmute yourself? Can you elaborate your question, sir? Professor Sarath, sir?
Sir, this is
Yes, sir,
Saroj.
please. Please, sir, please, sir.
Yes, sir. I want to ask about graphene materials for
Yeah,
marine
graphene. Yeah, you told that. Right? Nowadays, they are now using graphene as some reinforcement in major purpose in polymer matrix, all those things. Graphene is a good reinforcement, but cost-wise, it is you have to think about that. If you go upon reduction in particle size, it will cost more than 10K or 20,000. So you have to consider that. So that is the thing I'm asking, keep on telling you. So for what applications you are going to use, and based upon that, you go for selection of reinforcement. The cost has to be calculated, all those things. So since we have to enhance the mechanical properties, so that is the thing you need to consider before going to select the reinforcement. And you have to find the Young's modulus and the melting temperature and the properties which you are going to select for the reinforcement. So from that only you can be able to identify what type of reinforcement that you are going for present studies. So suppose go for marine applications, suppose go for aeronautical, suppose go for transportation industries. And you told that the heat treatment process in fins like that you told, right? Am I right? Hello?
Thank you, sir.
Yes, sir.
This is sir, one more last question, sir. This is a question from Professor Narendra Mohan, sir. Sir, can we use zinc in PMMC?
Zinc polymer metal matrix compound. Zinc?
No, zinc tin. No, previously I asked the question, sir, what are the other materials we can use? And he is asking continuation of that question. Can we use zinc tin in PMMC?
Actually, so zinc, I don't know about exactly how the strength of zinc, but only few literature papers are. So that is, I have seen that zinc-based metal matrix synthetic forms I found in some literatures, but only and that research is also told there will be some failure occurs in that by using zinc as a matrix material.
Thank you, sir.
So still if you need to reduce that tension, go for aluminum 8 series material. So that is the new generation of materials that can be used all over the world in future. 8 generation materials.
Thank you, sir. Almost we are reaching end time, sir. Now I will go with vote of thanks, sir.
Okay, thank you, sir.
I think. Is there any participants? Sir, please, you can ask.
I'm Sharad, sir.
Yes, sir. Please.
I have a question with sandwich composite, sir. Sandwich with aluminum 7000 series as a core material, and as a top material, I want to use some natural based composites. So how it could go, sir, for aerospace application?
So first of all, you are going for you are telling about laminates, right? Hello.
Sir, honeycomb, sir. Honeycomb structure, sir.
So honeycomb structure, I don't have experience in that. Sorry. Just refer some literatures related to that.
Thank you, sir. Actually, we are almost to the time, sir. Now I will go with vote of thanks, sir. It is very excellent presentation, sir. Thank you for your presentation, sir. You have started with the evolution of material, composite material. Why composites over metal? Metal matrix nanocomposites, some of the properties enhanced, challenges facing on development of MMNC, and the mechanism of nanocomposites, list of metallic matrices and reinforcements used for synthesizing nanocomposite, aluminum matrix composites, and the synthesis of boron carbide and boron nitride reinforced aluminum 707 hybrid composites using steel casting method, and the measurement of performance and testing parameters, XRD images, hardness, tensile strength, and composite strength of aluminum hybrid composites, corrosion resistance and wear properties, influence of microstructure and mechanical properties of titanium carbide reinforced magnesium nanocomposites, advantages of powder metallurgy method, experimental methodology. Then you have started with microstructure and SEM and XRD analysis of titanium carbide reinforced magnesium nanocomposites, hardness and compressive strength magnesium nanocomposites, corrosion resistance, synthesis and characterization of nanoglass particles in magnesium composites in solid phase method and liquid phase method using steel casting method. And finally, XRD nanoglass particles reinforced magnesium composites and the influence of nanoglass particles in compressive strength and tensile strength. Thank you very much, sir. It is a very, very detailed, informative session, sir. Thank you very much, sir. Thank you.
Thank you, sir. Thanks. So first of all, I have to thank the head of the management, head of the departments, the coordinators for giving this wonderful opportunity. I have to thank my friend Vamsi. So he called me and asked. So thanks. Special thanks to you. And I thank you all the participants to be patient. Thank you very much. Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Now I request the participants, our today morning session is over. We will meet once again 1:45 p.m. Next topic, afternoon topic is implementation of high performance thermoplastic polymer blended epoxy based nanocomposites reinforced with halloysite nanoclay for structural application by Professor E. Anand Kumar sir, Department of Engineering, FTBET University, Addis Ababa, Ethiopia. So I request all the participants, our today morning session is over. We will join with afternoon session 1:45 p.m. And one more information, today evening at 4 o'clock, we will give you some small assessment test. It is whatever we have listened to last 6 days. From that only, it is a very, very basic questions. Easily you can score more than 40%. Very easy questions only it is asked. So I request all the participants, please give an attempt to the assessment test, so that it will also be considered with the previous attendance and your marks also for getting the certificate. Thank you very much. It is very easy, simple test only, sir. Thank you all.
Okay.
Thank you so much.